is the last module of the basic linear regression. We're going to talk about metrics. We will talk about implementation, the details about how do you make it faster, why those choices we made, having those very concise matrix vector form of notations. Okay, so to get started, so this is a summary about the last component of our nutshell view is, so when we have this, the basic procedure of learning this f function, what do we looking for? What are our aims for that learned f function? So first, we emphasize many times is we want it to generalize well. And the second is we want this searching and learning and also prediction, all the steps, computational steps, as scalable and as efficient as it can. And the last, the goal of properties we aim for, we can kind of group them together, but there are a lot more. So it's very state of the art. People care, and there are many research about this. So how can we make a model robust? How can we make a model trustworthy? How can we make a model interpretable? And for many domains like safety concerned, just for example, this automated driving cars, if your model is very sensitive, think about the consequences, right? And also if your model are used in those automated maybe insurance rate quotation and maybe prediction of crime, and all those, it's the prediction itself, it's about trust. So it's not just about data, and you really need to guarantee as a tool builder person, it's actually in our shoulder to make our tool, the tools we generated, robust, trustworthy. So the third is very important, but we're not going to cover much in this class. We will have one invited speaker in the second half of the class to cover one related topic. All right, so let's come back to generalize well, which is the basic. It's really the basic aim we're looking for in our model. So when we talk about regression models, so similar to the classification example we showed before, and we, of course, we use training data, learn the model, then we apply that model on that pretend left out part of the reference data called the testing data. We use our predicted fx question mark and this true y question mark, which already been given by maybe manual labeler, maybe by the domain expert. We measure how our learned model behave in the future data. So when during the regression case, but what do we even mean error? So in this, sorry, there's a little overlay, but yeah. So right here, don't worry about that. So yeah, this part is a little bad. So in our code run through, and we actually find this. So it's really on this line. So in that basic linear regression from the scikit-learn, the Jupyter Notebooks cell run, and it actually uses, so let's again review. So we use the fit function to learn. So give me a second. Yeah. So we used fit function to learn, and then we use prediction function to predict, and then the mean squared error is one of the possible measure. So which is exactly a function from that metric module called mean squared error. And there's another function called R2. So the simplest metric we can think about is, so this is our testing data, right? We actually draw this. And this is one testing data. And we can see this is X test 1. And in fact, I mean, it's representing the X, right? So, and this point, so this is xt1 and yt1. And the predicted yt1 hat is exactly these X positions. What is the line predicts what should be the Y. And then the error, if we used something called mean absolute values, it's really just yt minus yt1 minus yt1 hat, and then take absolute differences, which is the magnitude of this connecting line among the 2 points. And then you can just sum over all of the testing points, and I from 1 to t test, and then we can make the subscript as ti. So this is one kind of most basic metric called mean absolute error. It's just the absolute differences. And you can also take a square. If you take a square of this, summation over, oh, there's a mean value, so I should do a 1 over the testing size because it's a mean, right? So it needs to be normalized by the number of testing points. Yeah, so this is called mean absolute error, and then the mean square error, it's almost the same as the sum of square error in the training cost function. The only difference is it's just you don't do absolute values, you actually do the quadratic. Sorry. S then yti minus yti hat, take a square. So you can tell the square error actually penalize more or show more if on those points who have bigger differences. Yeah, so there are actually many more. So this is the link of scikit-learn and the model evaluations, and this section is the regression. So it's not just what we had there, not just the mean absolute error. They have the explained variance, max error, like really many more. And then one of them is R2, which you can check out the equation by yourself. I don't want to talk about it here. So different metrics really care about different properties. It depends on your domain. What is the task you care? Is it care like it really care to try to have as close as it can, or it want to have smaller variance, or it want to have that max error, just whoever in the testing data give me the biggest error. I use that as the measure of generalization. So if your data is super noisy, think about this. And this max error not necessarily be a very good friend. So consider your data, consider the application, and pick the good metrics that exhibit what you want. What do you mean generalize well in your specific domain or in your specific task? All right, this is about metrics. And then the next second property we want our model is it can be computationally scalable, it can scale to large amount of data, it should be efficient. And this is really my favorite topic. So let's take a look. So what is the operation in the linear regression? Again, 2 modes. We have a training mode, we have a testing mode. So even though we have done that's really complicated derivation, but when it boils down in the end, I mean, if we use this closed form normal equation-based solution, what we really do is really just this equation, the first equation during training, and the second equation during testing. And this is all it really is. I mean, in my computation, right? The fit function, and this is the fit function, and this is the predict function. So I want this operations is as efficient as I can. This doesn't look like, so this matrix or vector form notation. So why can't I just write everything like what I did in our simple examples? I just write this area function as plus, 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 plus on those 3 points I had, right? If you still remember. And the reason is all this type of form, matrix vector form, it's related to how the underlying computer architecture, how your library make use of the computer architectures. So let's just make the simplest naive matrix multiplication as example. So this is a very generic form performing matrix multiplication. Let's just assume all the ABC matrices are just n times n matrix. And it's actually pretty easy to perform this very general form of matrix multiplication. If you do this for loop go over every entry of the C. The C is my target matrix, right? Then there are how many for? I mean, I need to go over every row and every column, actually every entry in the C matrix, right? Which means there are n times n operation. It's really these two lines. So these two lines decides there are n times n runnings of this parts. And this part is the generation of that specific Cij. And to calculate Cij, you have to AI vector, row vector, this AI row vector to do inner product with this Bj column vector. So if this is size n and this is size n, so I hope you still remember, it's really just summation. It's an inner product of every entries here. So it's like A, I, question mark, and B, this, and then it's inner product, right? So what is inner product? Just you multiply all those corresponding elements from the first to the last, and then you do a summation. So what is this inner product operation computational cost? If you know it, please type yes, ON. This is an ON cost. All right, so this is ON, and then you need to do this calculation for every entry in the Cij. There are total n times n in the C matrix, which means what? A naive 4 levels of loop calculation, this kind of implementation needs to cost ON cubed. And this is bad, in fact. You can also do the similar to figure out we need 3 times n quadratic memory cost. So this is the time cost. And this is the space cost. And this is bad. Okay, so this is just a naive implementation, which is exactly what I have done on our simple examples, right? I just do sum, right? All right, so let's do it more concretely on the training in the linear regression. I put the equation copied here. So different from the previous, which is n times n matrix, here we have, so our X train matrix, we just assume it's n times p, and which means extreme transposition is p times n. So that's why I write p times n here. A p times n matrix times n times p matrix. What is the cost here? We can do exactly the same as the previous page. We are generating, so this generated matrix is p times p size, right? Which means I need to fill in p times p entries. And each one of that entry requires a row and column vector in the product, which is a own cost. It's cost n. So that's the reason why x transposition x, it's an OP quadratic n time cost operation, a naive version. And then I will not tell you why, like take inversion is p cubed. You can actually check it out, do it or maybe do it by yourself. Not that difficult too. So which means our training in when you put them together, the cost is O np quadratic plus p cubed. And in most cases, we have much larger n than the p, which means what? So our training operation is dominated by these items. But in many biomedical data, in fact, it's p much larger than n. And in those data, actually your cost is dominated by this p cubed term. But this is all naive way, right? Okay, but this is totally not how the state of the art computer implements all those computations. And the state of the art, there are three things people actually considered and make the operation much, much faster. So we can split the related factors into three different kinds. So there are many data parallelization you actually can do. And then when your data can be parallelized, operation can be parallelized, then you can make use of the CPU SIMD, SIMD architecture, or the multi-threading architecture, and now it's GPU parallelization. So that's the first people have done a lot to speed it up for the operation we have done there. The other is the memory hierarchy or the locality consideration. And the third is, so we use extremely naive algorithm, but they're much better algorithms like strengthens algorithm or something called CW or CW alike. I think if you're taking algorithm class or you already finished the algorithm class, you may already learn the strengthen in your algorithm class. All right, let's take a look at each one of them one at a time. So what do I mean data parallelization, right? Let's take a look at what is the CPU single instruction multi-data architecture. So this is the most naive way to talk about this. So if I want to do a x plus y, I mean, assuming there are multiple, like in this example, x3, x2, x1, x0, I just do a vector summation, right? So to do this vector summation, if I do like what I did in my last time's simple example, I will do a for loop, then just add, because that's all I wrote in the previous notation, right? Think about what did I write about that error calculation for the regression prediction? I did I from 1 to, in this case, is actually 0 to 3, and then I do xi plus yi. And that's exactly the way I did in previously, and then which reflected in this cooperation, which is bad. I hope now you understand it's bad, because there's so many like data parallelization actually you can do here. The reason is when doing summation x1 plus y1, it really doesn't matter. My operation doesn't block x0 plus y0. It doesn't block x3 plus Y3, right? They are totally independent tasks. Now, why should I do a for loop, make it sequential? As long as I can make it parallel, I should just do it parallel if my computer allows it. And so a lot of this type of parallelization computation, it's already being supported in the CPU and even more actually in the GPU. So this, the CPU one is called SIMD. Not sure if you have learned in your architecture class, but it's just a very basic architecture. And then state the art, then something called their SSE1, SSE2. There are actually a lot more advanced versions, but just the whole thing is more about data parallelization. And we are going to cover a little bit more about GPU parallelization, which is really best for the matrix multiplication. Okay, so that's the first concern. How do you parallelization do those can be parallelized, those operations or those decoupled operations to make them all run at the same time? The other concern is about memory hierarchy. So I hope you actually learned this a little bit in your architecture class or in your OS class. So look at this. So in the processor, and so we have this different levels of memory, right? Start from this really much faster on-chip cache to the second level SRAM, DRAM. They're actually even faster. They're middle version there. I did not put it there because this is an older slides. So all those different level of memory, architectures, their speed varies. The most trend is when if they're super fast, they're normally smaller. And then it really depends on your data. I mean, especially when we are doing this very data-rich type of computation, it's highly likely it's not just possible to just fit into this on-chip cache, which is a little bit just kilobytes or megabytes, or maybe even gigabytes. So in a lot of cases, even the DRAM is not enough to fit your data there. Then you have to design smarter algorithm to think about this. And then there's also other considerations like are you touching the data or sequentially? I mean, when you're doing matrix operations, how to group those operation touches those data located in similar locations in the memory. And if you can design well, those can speed up your algorithms a lot. So that's the second consideration, memory, and locality, spatial locality and temporal locality is the thing you really need to consider to have a smarter algorithm. All right, so that's the second consideration. And then the last is, okay, we actually can also have a better algorithm, even if we're using similar architectures. So for example, the school book matrix multiplication, which is the one we just showed you, it's O(n) cubed. And the strengthens method can reduce that power term from 3 to 2.8. So this sounds very small, right? But when your n is like millions or even a thousands, and this helps a lot, that smaller power term. And there's another better algorithm like CW-alike method, improved it even more, 2.3. And so last class, I did this matrix. In fact, what I did in solving that JWB, if you still remember, and I set this JWB equals to 0, and then essentially I did a matrix inversion. And that's a school book type of solver, which is this Gaussian Jordan elimination method, which cost O(n) cubed. But they're much better method, similar to the matrix multiplication. The algorithm are similar, just a little bit reshifting. All right, so this is the algorithm, and maybe some of you already learned it in your algorithm class. Okay, so everything I told you sounds cool, right? But there are so many details. I mean, the memory details is about the specific computer. I mean, the OS, the architecture, that type of SIEM's architecture or GPU. It's about your current computer, also the library using that computer, and the algorithm. I mean, there's also variation of the algorithm, right? So as a general user, then people come out just to help the general user kind of hide all those details through this library API interface. And that's how we are normally used. NumPy is the Python wrapper library of this industry standard called BLAS, Basic Linear Algebra Subroutines. And it's really like, so it has this like black box type of middle API, and you just use it kind of similar, but there's so many variations, depends on the vendor, depends on that supply optimized implementations. So it's quite complex. I mean, so if you're not going to, if those, your method is not like extremely bad, you just have to dig into the library implementation. You normally just stay in the library level. You just use these libraries. And there kind of history of variation of BLAS, I mean, starting from vector operation, that's BLAS1. Then BLAS2 is a matrix vector operation. BLAS3 is matrix operation. And then we are mostly using the BLAS3. All right. So the pretty classic is the LPAC, and okay. So now I think this page is a restating of the previous page. There's more. It's a Wikipedia page I got from Wikipedia, and just keep in mind, I mean, even the same operation, because of the different library underlying there, and the performance actually have some differences. For example, you may already know about something called Intel MKL, and the version of the MKL library and AMD's ACML library on different computers, actually there is some kind of noticeable differences. And this y-axis is the Mac flops numbers. So, but this again depends on task, also depends on the computer, depends on implementation. All right. So I think this is all I want to cover about the last module. And we covered everything about the basics in linear regression. And I will close the recording